Okay, so in this video we're going to start wrapping up this unit. Just to give a brief recap of all of the things we've learned in this unit, we started off by talking about the Thomson model of the atom, the Geiger-Morrison experiment, and how the results of that experiment led to the development of the Rutherford model of the atom, which is the first nuclear model of the atom. That is the first model of the atom which contained the nucleus. We talked about, what are the particles inside the nucleus, how small is the nucleus relative to the atom, what are nucleons. Remember, nucleon is just a generic term for particles inside the nucleus, aka protons and neutrons. And so protons and neutrons are both examples of nucleons because they both exist inside the nucleus. And then we also talked about nuclear notation and how to write that. After that, we moved on to nuclear stability. We talked about, the different fundamental forces. There's 4 fundamental forces in the universe. 2 of them have to do with nuclear stability, and we talked about how that strong nuclear force and the electrical force, the Coulomb force, have to be in balance in order for an atom to be stable. And if they're not, then you have a radioactive atom. Then we talked about different types of radioactive decay, alpha, beta, and gamma, and the properties of their respective radiation particles. The alpha particle, of course, is a helium nucleus. The beta particle, well, we now know there's 2 types of beta particles, beta plus, which is a positron, that's a positive electron, and beta minus, which is an electron. And then the gamma particle, which is a high-energy photon, which is a particle of light. And we'll talk more about photons here in a little bit. After that, we learned how to write nuclear equations specifically for radioactive decay. There's other types of nuclear equations that we will see in the next unit. But so far, the only types of nuclear equations you should be able to do relate to radioactive decay. And then we talked about the law of radioactivity, how radioactivity is a random and spontaneous process, and then the concept of half-life and activity, and how that is kind of like an exponential decay type of thing. And so now we're going to return to our discussion of models of the atom to start finishing up the unit. Before we get to that, we're going to take a brief detour. I'm just going to make this bigger so you can see this and add this to your notes as you go. And let me just read what it says in the notes. It says, although the Rutherford model of the atom correctly contained a nucleus, it was unable to explain several different observations, one of which was the existence of atomic spectra. By the way, spectra is the plural of spectrum, and the study of these atomic spectra was called spectroscopy, and it was a major area of research as early as the 1600s, the mid-1600s. And we'll talk about what atomic spectrum means, but basically there's 2 types. There's what's called emission spectra and absorption spectra. I've been saying spectra a lot, so let me get into what it is we're talking about here. Now you might ask yourself, by the way, what does this have to do with models of the atom? What we're going to talk about is what are the limitations of the Rutherford model of the atom. There's 2 main ones we're going to talk about, and the first one relates to not being able to explain this known phenomena of atomic spectrum. So, what are atomic spectra? Well, so you might know from playing with a prism as a child that if you take white light from, let's say, a light bulb or a flashlight or the sun or whatever, if you pass it through a prism kind of breaks the light up into its individual pieces, into its individual wavelengths, and you get what's called a continuous spectrum. Okay, meaning here's a white light going into the prism, here it is coming out, and you can see when it comes out, it's kind of split up. And if you were to project this onto a wall or a piece of paper, you would see something like this. Okay, so this is called a continuous spectrum. It's a spectrum because it's a long range of things, and it's continuous because, well, there's no holes in the spectrum. Now, continuous spectrum comes from white light, breaking white light up into its individual pieces. Okay, so that's just to start with. That not anything to do with atomic spectra yet. Here's where the atomic spectra come in. It was discovered that if you take a tube of gas, and this was discovered in the, hundreds of years ago, but if you take a tube of gas and you either heat it up to a high temperature, you burn it, or you run electricity through it, the gas actually glows, it ionizes, and it emits light, and it begins to glow. And in this picture, what you're looking at is different tubes of gas. This is helium, this is neon, argon, krypton, xenon. and they're in tubes that are being subjected to electricity, a high voltage. Now, normally in class I would show this to you in a real-life demonstration, but the pictures will have to suffice. If you've ever seen neon lights, neon is very commonly used in lights because it gives off a very distinctive red glow when you run electricity through it. Okay, so that's basically where neon lights come from. It's basically just a tube with neon gas in it, and they run electricity through it, and the gas glows. Now, unlike white light, when you take the light coming off of this glowing gas and you put it through a prism, you don't get a continuous spectrum. Okay, now the device is not actually called a prism, but it basically functions as a prism. It's basically called a spectroscope, which essentially acts as a prism. And it turns out if you take the light coming off of a gas, let me back up here for a second. Okay, if you look at the light coming off of a gas, you actually get these individual lines. And so rather than getting this continuous spectrum that you get with white light, you only get these lines that look like this. And this is what's known as an emission spectrum. Okay, so again, pause it here if you need to add this to your notes. A lot of people get confused between emission and absorption spectra, but it's very easy to remember. An emission spectrum is what you would get from a gas that is emitting light. Now again, how do you get the gas to give off light? Either you heat it up or you run electricity through it. You might have seen in your chemistry class a demonstration where you see different colors of flame. That comes from taking different salts and putting them in fire, and then they give off different colors of light, and it's a very cool demonstration. So one example of a way that you can get light to be produced from different elements is by heating it up. The other way is by running electricity through it. And we'll talk about why that is later. But again, this is an example of an emission spectrum, and so this is the emission spectrum for barium gas. And it says at the bottom, an emission spectrum is an elemental fingerprint. Now, normally when people think of fingerprints, they think of something that humans have that's unique to each individual human. And the analogy here is that it turns out each element has a unique set of emission spectrum lines. We'll come back to that in a second. Okay, this is basically just another slide repeating the same information and kind of showing you how would you see this emission spectrum. Basically, you take your tube of gas, you run electricity through it. That's the easiest way. You take the light coming off it, you put it through a spectrometer or a prism or whatever you want to call it, and it breaks it up. And if you project it on a screen, then you get these individual lines right here. Okay, and with each element having a unique set of lines. Now, again, when I say a unique set of lines, here is just an example of spectral lines, emission spectral lines for different elements. We have lithium, we have sodium, potassium, rubidium, cesium, helium, neon. Each element on the periodic table has a unique set of emission spectrum lines. In fact, if you're ever in my classroom again, if you take a look at the periodic table I have at the front of my classroom, it's a periodic table that shows the emission lines for each individual element on the periodic table. Okay, so basically what that means is if you take, let's say, an unknown gas and you either burn it or you run electricity through it, you can figure out what gas it is just by looking at the color of the light that comes out, breaking it up into its individual pieces like this, and looking at where the lines are, because again, each unique element has its own set of lines. Okay, so these are emission spectral lines for different elements. Okay. Now, moving on in the notes, it had been discovered in the 1800s that each element has a unique emission spectrum, kind of like an elemental fingerprint. We talked about that before. In fact, this is kind of a random fun fact. It turns out that in the 1860s, when they were looking at the sun and trying to figure out what element the sun is, or what elements make up the sun, they saw, hydrogen. They saw some other lines they recognized, but they saw a set of lines that they couldn't identify that had never been discovered in a laboratory on Earth. And so basically what they found was a brand new element. And because they found that element in the sun, they named it after the sun god Helios, and they call that element helium. And so fun fact, helium was actually discovered on the sun before it was discovered on Earth. Of course, nowadays we know we also have helium here on Earth, but it was actually discovered on the sun first. Okay, just from the light given off by the sun, which is kind of cool, actually. So that's where helium gets its name from Helios. And then this is basically just another slide showing the same information. Normally we would do a demonstration here. Okay, so that is emission spectra. Now, absorption spectra is kind of the opposite thing. And so when you talk about an emission spectra, you're talking about the gas giving off light itself. Now, we know that if you take a white light and you break it up with a prism or a spectrometer, you get a continuous spectra. We saw that before. Likewise, we know if you take a gas and you make it give off its own light by heating it up or putting electricity through it, you get an emission spectrum. Well, it turns out if you take that same gas and you put white light through the gas and then you put it through a prism, you don't get a continuous spectrum anymore. Somehow by going through the gas before going through the prism, it loses some lines and you get what's called an absorption spectrum. And that's what you see here in this picture. Let me see if I can make it bigger. Okay, so this is showing you the difference between a continuous spectrum, an absorption spectrum, and an emission spectrum. Okay, with the absorption spectrum, you take white light, which would be a continuous spectrum by itself, pass it through the gas, then pass it through the spectrometer, and you get an absorption spectrum. And so an absorption spectrum looks almost like a continuous spectrum, but it has these black lines, these missing lines. Okay, so that's the difference between an emission spectrum and an absorption spectrum. Okay, now this is showing you the emission spectrum from hydrogen versus the absorption spectrum from hydrogen. So in other words, the top one you would get by taking a tube of hydrogen, running electricity through it, taking the light, passing it through a prism, whatever. The absorption spectrum you would get by taking a white light, which again would normally be a continuous spectrum on itself, passing it through the hydrogen, and then seeing what comes out the other end after you pass it through a prism. And if you look at the hydrogen spectrum, the emission and the absorption spectrum, you'll see that they're almost mirror images of each other, or negative images of each other. In other words, the lines that appear in the emission spectrum for hydrogen are also the same lines that are missing in the absorption spectrum from hydrogen. Okay, so something, again, is very special about these unique lines and where they lie. Now, just random applications of atomic spectra. Again, please pause it here if you need to add any of this information to your notes. Okay, so two applications of atomic spectra. One of those we kind of alluded to before, but you can basically take any object you want or any gas you want, and you can find out what elements are in that gas or object by basically causing it to emit light, usually by burning or, again, passing electricity through it. And then by analyzing the light that comes out the other side, you can identify what elements make up that mystery object. Okay, now a more specialized application of this would be what's called stellar spectra, which is basically looking at different stars and looking at their spectra. And what we can do with that information is we can actually find out lots of cool things from that. But one of the things is we can find out what elements make up different stars. And so that's how we know that stars are mostly made of hydrogen and helium with some amounts of other heavier elements. And so if you ever wanted to know how do we know that the sun is made of hydrogen, it's all from the light it gives off. Now we're not going to get into it now, but we'll talk about in IB Physics 2 how you can also use the atomic spectrum not only to figure out the chemical composition of stars, but also to figure out how fast stars are moving either towards us or away from us. And we're not going to talk about that now because it has to do with some more complicated things that I don't want to get into. But we can get a lot of information from stellar spectrum. Okay, so atomic spectra in general, very, very cool kind of thing in physics that has a lot of useful applications. Normally we would check out some of these videos. I will put the link in so you can watch them. Now, okay, so you might be asking yourself, atomic spectra seem cool and exciting. We can play detective by looking at light, basically. What does that have to do with atomic physics? Well, let's get back to that. Now, we left off talking about the Rutherford model of the atom and how the Rutherford model improves upon the Thomson model of the atom, which it does because it has a nucleus, and the plum pudding model did not have a nucleus. And so, we talked about how in science you're always trying to build better and better and better models based off of the evidence you have. Rutherford model was an improvement on the Thomson model, but it had its own issues. Here are two significant limitations of the Rutherford model. First of all, the Rutherford model basically gave us no way to explain the existence of atomic spectra. Now remember, atomic spectra were known to exist even in the 1800s. Rutherford model was developed in the early 1900s, and even, decades later, the Rutherford model was not able to explain why do we have atomic spectra. We know they exist, but why? Okay. Ideally, a new model in physics should be able to explain current observations. Rutherford model couldn't do that. Now, here is kind of a more important limitation of the Rutherford model. You do need to know both of these. But the more important issue with the Rutherford model is that atoms are stable. And we know atoms are stable because the universe exists, and everything in the universe is made of atoms. However, and this is something you want to add to your notes, we're not going to talk about the why this is, but according to the known laws of physics at the time, the laws of electrodynamics, if you have an electron that is orbiting around a proton or orbiting around a positively charged nucleus. Rutherford didn't know what was inside the nucleus, but he knew it was positive. But if you have an electron that is accelerating, okay, anytime you have a charge that is accelerating, it radiates energy. Now, again, you don't need to know why that is. That's just a random fact that you need to know for the class. But if you have any charged particle that is accelerating, it radiates energy. And so the electron orbiting around the nucleus like a planet orbits around the sun in Rutherford's model should radiate energy. Just really briefly, I'll mention, you might ask yourself, why is an electron orbiting, why would that be accelerating? Well, if it's moving in circular motion, it has centripetal acceleration, and so the electron in orbit would count as an accelerating charge, and therefore should radiate energy. And as it loses energy, the electron is going to spiral into the nucleus, and then when it meets the nucleus, the atom is basically going to no longer exist, it's going to go poof, and that means that atoms cannot exist, which means the universe cannot exist. Now, obviously, that's not correct because atoms do exist, and so if this is what the Rutherford model predicts would happen, either there is a problem with the laws of electrodynamics, which, probably not, or there's a problem with the Rutherford model, which there is, okay? And so we'll get into the next model of the atom, which does a little bit to address this issue of stability. And so those are the two main limitations of the Rutherford model of the atom. Number one, unable to explain either emission or absorption spectra, and unable to maintain stability because electrons accelerating charges should continuously radiate energy and spiral into the nucleus, and therefore the atom would no longer exist. Okay, and so just really quickly, I'm going to show you this video clip. I'm going to mute that noise. Okay, so I'm not going to go through this whole video. This is just going through the different models of the atom. Geiger-Marson experiment. And I'm going to kind of fast forward. Here's the issue with the Rutherford model of the atom. Okay, and you can see the electron orbiting the nucleus in circular motion. Because it's accelerating, it should be losing energy. And as it loses energy, it should spiral into the nucleus like this. There's the electron losing that energy, and it gets closer and closer and closer and closer to the nucleus, and then boom. Okay, the atom ceases to exist. Now, again, that obviously doesn't happen, and so that's why we know the Rutherford model is wrong, or at least that's one issue with the Rutherford model. It says right here, in the video, Rutherford model cannot account for stability of the atom. Plus, it can't explain atomic spectra, which is also an issue. Okay, so it was suggested that because the spectral lines have discrete values, that maybe atoms can only have certain discrete energy values. Okay, unfortunately, Rutherford's model was not able to explain any of that, and so that's going to lead us to Bohr's model of the atom. Now, I will link this video in real quick, just so you can see. And let me kind of go ahead really quickly. I just want you to leave off adding some things to your notes. This is basically a few years after Geiger-Morrison experiment, after the Rutherford model had been proposed. This physicist named Niels Bohr postulated his own model of the atom. Now, I want you to put these postulates in to your notes, and then this is going to be our starting off point for our next video, talking about the Bohr model of the atom and how it's able to explain things like atomic spectra and nuclear stability. Now, I know there's a lot to write here. I apologize for that, but these are 4 postulates that we'll kind of go through one at a time, and hopefully they make sense. At least some of them make sense initially. Okay, so please let me know if you have any questions, and I will see you guys in the next video.